All right, welcome everybody. So recording has started. You know, yesterday we started in on the discussion about reviewing mechanics, and that starts with defining motion. And so the first slide on your sheet is our definitions of motion, right? So we talked about the four things that we look for, three things really: displacement, velocity, and acceleration. But we said that speed and velocity obviously have a lot of similarities there. We talked about the difference between vector scalar. We talked about how the sign of things for like velocity indicates the direction, but then acceleration, we talked about how the sign really determines whether it's speeding up or whether it's slowing down. Okay? So we talked about instantaneous versus average, right? What's happening right now versus what's happening over a larger period of time. The next page, this top of the back of the first page, gets into frame of reference. I'm not going to talk about this a whole lot, but the important thing to remember here is that how we make these measurements does depend on where we make them from, right? Sometimes the frame of reference is as simple as setting up a reference point and then calling one direction positive and the other direction negative, but sometimes, like if we have an observer that isn't stationary, like we have an observer in this car observing this car, he's going to observe the motion of the car different than, say, somebody who's just standing on the side of the road, right? Like this situation over here. If we ask this guy what this car's velocity is, he would say 30 meters per second, because that's the velocity of the car relative to somebody standing still. But if you ask the person in the car what this car's velocity is, they would only reply with 5 meters per second, because now he's moving, so his frame of reference is different than the observer, right? The one thing to keep in mind, though, is that even though the frame of reference may change, that doesn't change the motion of the car. This car is still moving at the same velocity regardless of how we describe it. It doesn't change the motion, it just changes how we describe that motion. Okay? All right. Big part of this unit deals with graphs, graphical representation of motion. There's two types of graphs that we normally look at. One is a position versus time graph, and one is a velocity versus time graph. Here in the description, they do mention acceleration versus time graphs, but we don't look at those a whole lot because they don't tell us a whole lot. So there's two things that we can look at on a graph. First is the gradient, and we said that's IB's fancy way of saying the slope, right? The second one is the area underneath that graph, and when we say the area under the graph, we're talking about the area between the graph itself and the x-axis. Depending on what graph we're talking about, sometimes that can be above the x-axis, sometimes it can be below the x-axis, but it's all still important information. For most of the graphs that we're going to look at, especially at the beginning here, they're going to be fairly smooth or fairly straight graphs. And so finding areas is going to be as simple as taking the area of a triangle or a rectangle or something like that. When you get into more advanced study, we can use calculus to find the area underneath a curved graph, taking the integral function. You're not responsible for that in any way, shape, or form, but we can do that so we can analyze something more complex. Okay? All right. Here is the three types of graphs, okay? So we start off with a displacement time graph or a position time graph, right? Like its name suggests, it tells us the position versus the time, right? Where is this object at a certain point in time, okay? The gradient of a displacement time graph is the velocity. So the slope on this graph tells us the velocity. And if you think about it, right here, I'll zoom in for you guys, but you can't really see it on the video. But well, I suppose we could. Hold on. Can I? View. Do I have a zoom here? Page zoom with pen. That is not what I want. This is gonna be good to watch, you know, like me figuring out if I can zoom or not, but yeah. All right, here we'll zoom in manually here in the room. All right, so on this graph, right, displacement on the y-axis, time on the x-axis. When we have these graphs, displacement time, velocity time, acceleration time, time's always going to be on the x-axis, and then whatever it is we're measuring is going to be on the y-axis. Okay, so for this graph here, during this first section, in the first 4 seconds, the object goes from being at the reference point, 0 position, to being 20 meters away from that reference point, right? So we can calculate its average velocity because we know how far it went, 20 meters. We know the time that it took to go that distance, 4 seconds. So 20 meters divided by 5 seconds, we have an average velocity of 5 meters per second, right? Does that make sense? Okay. That's also the slope of this graph because slope is rise over run, right? The rise of this graph is 20 meters. The run of this graph is 4 seconds. So that's mathematically the slope, and the calculation of the average velocity is exactly the same calculation. So the slope on a displacement graph gives us the velocity, right? The fact that this is a straight line means that the slope is constant, and that also means that the speed is constant, or the velocity is constant. Here, if we have a horizontal line, we know from math class that horizontal lines have 0 slope, and as a result, that represents 0 velocity, 0 motion, right? Because if we look at the position or the displacement, it never changes over this entire 3-second interval. If position isn't changing, there's no velocity, right? It's not moving. Finally, this last little section here, right? It's a steeper slope because now that person covers the 20 meters, but in only 1 second instead of the 4 seconds that it took in the original part. That produces a steeper slope, but that correlates to a faster velocity, right? Here, still constant slope, but the slope is different from this one because this has a positive slope and this has a negative slope. That correlates to positive velocity versus negative velocity, moving back in the other direction. Yeah? This graph down at the bottom, excuse me, is also a displacement time graph. Sorry. This graph at the bottom is also a displacement time graph, but its velocity is not constant because the graph is curved. So curved displacement graphs you had to do it. So curved displacement graphs correlate to motions that have changing velocity. This, like it says here, object thrown vertically upwards. The slope here is very steep, but as the graph goes up, its slope gradually decreases and decreases and decreases and decreases, especially if we draw a tangent line to that graph. Does that make sense? The tangent line, right? The tangent line represents the slope at that particular point, so it's the instantaneous velocity. But here, I don't remember, you guys might not have gotten to this yet, but when you get to calculus, but I think maybe when you do pre-calc as well, the slope of this graph at this point is what? 0, meaning that the velocity at that point is 0 as well, right? It's an inflection point, right? It goes from having positive slope to negative slope, which it correlates to an object going from one direction into another direction. An object that we throw upwards gradually slows down And then what does it have to do at the top? What happens to that object before it starts coming down? What does it do? And then stops just for an instant, but it does stop because one, it has to go from having a positive velocity to having a negative velocity. In order to do that, you have to go through zero. But also two, right, if we look at the graph, the slope gradually decreases and decreases and decreases, still positively sloping, upwardly sloping until it gets to here. That's zero slope, zero velocity. Then the slope becomes negative from that point forward, so that indicates it's going in the other direction. Okay. Good there? All right, the middle section, velocity time graphs. Velocity time graphs actually can be used to tell us two things. Oh, in this page, we said there's two things that we can look for in graphs. One is finding the slope. Two is finding the area. I know I'm zoomed in, but finding the slope, finding the area. On a displacement graph, the slope is the velocity, but if we were to find, like, if we were to find the area of this triangle right here, this rectangle right here, and then this triangle right here, physically that has no meaning. Like, mathematically we could do it, but physically it doesn't mean anything. When we get to the velocity, that changes. So the slope on a velocity graph tells us the acceleration. But the area under the curve, or the area that we calculate in this space here, would actually give us the displacement that occurs during that time. Okay? So, right? Come on, there we go. All right, so this graph here and the previous graph on displacement look really similar. In fact, the numbers are all exactly the same, but the only thing that changes is the label over on the y-axis, and now it's velocity instead of displacement. So during this section right here, there's still a constant slope, but what does that mean physically is happening? It's accelerating because now the y-axis is velocity, right? So now instead of it gradually increasing displacement like it did on the first graph, it's gradually increasing velocity. So it's going faster and faster and faster and faster and faster and faster. Because it's a constant slope, that means it has a constant acceleration, right? It's gradually getting faster, but it's getting faster by the same amount each time interval. Okay? Horizontal sections of this graph now represent not constant position, but constant velocity. This object is still moving from the interval 4 seconds to 7 seconds because it has a velocity. The velocity just does not change over that time interval. And then finally, from here to here, what's happening to that velocity? From the 7 seconds to the 8 seconds, what's happening to the velocity here? Well, it goes from being 20 to eventually being what? 0. So physically, what's happening there? Yes, what kind of acceleration? Okay, so negative acceleration. Physically, if we were looking at an object that went from 20 meters per second to 0 meters per second, what is that object doing? Well, it's slowing down, right? Say again? Not yet. Okay? Has to stop first. On this graph, what has to happen for an object to change directions? And then go negative. Because on this graph, positive and negative does tell us the direction, right? This is positive velocity. It's an increasing positive velocity, but this is still positive velocity, it's just decreasing. A positive velocity that's decreasing is still moving in the same direction, it's just slowing down. So this whole graph right here represents motion in the same direction. Okay? It speeds up, it's constant, then it slows down, but it's still the same direction. Different than this graph, right? This is a velocity graph. The first section of this graph, what's happening to the velocity in this section right through here? Not yet. What's the initial velocity in this graph? 9. It's 9, right? What's the velocity at that point that I just highlighted in pink? 0. So if something goes from positive 9 meters per second to 0, physically, what did it do? Slowed down, right? Here, right? That velocity is 0, right? But then the velocity here is what? Negative 9. What is happening to an object that goes from 0 meters per second to negative 9 meters per second? It's speeding up. It's just speeding up which way? Negative direction, right? These two graphs here are the same motion, just one's displacement, one's velocity. As we throw an object up in the air, what happens to its velocity? It slows down until it reaches, at the top, then turns around, starts accelerating again in the negative direction, right? What do we notice about the slope of this graph? What do we notice about the slope of this graph the entire time? And that means that what's constant if it has a constant slope? What does slope on a velocity graph tell you? Acceleration. This has a constant acceleration because when you throw a ball up in the air, what's affecting its motion? Gravity, which causes a constant acceleration, right? Does that make sense? We okay with that? And then if we were to slide over the last picture on the right, we would see that the acceleration here is in fact constant the entire time. It doesn't change because gravity causes that constant acceleration. Okay? Good there? Okay with those graphs? All right. The next section of this unit deals with equations of uniform motion. And when we say uniform motion, that generally speaking means uniform acceleration. So, you guys can't see that. So, this is broken up kind of weird in your packet because the book was kind of broken up weird. I tried to group these things together here so we can talk about the same things. So when it says equations of uniform motion, when the uniform motion requires that it's uniform acceleration. Okay, the acceleration has to be constant. That could be a constant acceleration of 9.81 if we're talking about gravity, or it could be a constant acceleration of 0 if an object is not speeding up or slowing down, right? These relationships, these equations work as long as the acceleration is constant. Okay? Sound good? When we talk about these equations of constant acceleration, there are 5 descriptors of the motion that we look for, that we look to measure. We use the lowercase letter u to represent the initial velocity. We use the lowercase letter v to represent the final velocity. A is the acceleration, t is the time that elapses, and then s is the distance traveled, although that's not true. It actually should be displacement. It would be distance traveled as long as we didn't do what? Change direction. Even if we're... Alright, so when we talk about an object moving with constant acceleration, we look for to measure these 5 things: initial velocity, final velocity, acceleration, time, and then the displacement. Okay? Then what we find is that these mathematical relationships, even though I drew off the page, these mathematical relationships hold true for objects moving at a constant velocity. This gives you a derivation of those equations. You're not going to need to derive the equations on an exam. You need to know how to use them. They will be in your reference packet. They're part of the information that IB provides for you. You just need to know how to use them. Okay? So, as we close in on the end of the period here, I think that's good for today. Monday, I have a set of questions that deals with these things. We can start working on those together on Monday. Okay?